Good afternoon, everybody, and welcome to this session of PyCon AU. Our next speaker is Michael Kelly. Oi, shush. Shush. Our next speaker is Michael Kelly, who will be talking to us about orchestrating things with Python and AWS. Please make him feel welcome.
Can everyone hear me? All good? Okay, good afternoon, everyone. My name is Michael Kelly. Before we kick off, I would just like to say thank you to PyCon for having me here, and thank you to Versant, who I work for letting me attend great conferences like this one. A little bit about me. I'm a team lead for a cloud product division at Versant, focusing on infrastructure orchestration. Versant provides auto-scaling, auto-healing cloud architecture solutions in AWS. We're always looking for dedicated cloud engineers, so if you know anyone who's looking, I'll be around after the talk. Just let me know and I'd be happy to put you in contact with someone. So why did I choose this subject? AWS is a big part of my career at the moment. Versant is almost exclusively working with the AWS platform for delivering cloud solutions. Over the last 9 months, I've been working with step functions, and compared to many other ways I've tried to orchestrate the build and teardown of applications, step functions have by far been the most powerful, cheapest, and complete solution. The service is very powerful and you can do a lot with it, but it's very easy to get yourself stuck. So I hope to go through some of the ways that can happen today and provide some service native patterns to scale more gracefully and build great services. So this talk is primarily about orchestrating tasks where you're already hosting resources in AWS. Still this link? No, okay, it's all good. About orchestrating tasks, we're already hosting the resources in AWS. When I initially got into Python a while ago, I found it to be a pretty gentle learning curve for beginners. So using Lambda and step functions, I also found this to be the case. With Lambda, it's very easy to build something that's useful by knowing some initial key concepts about the service and about the Python programming language. Step functions are basically just an extra layer on top of all that and requires a few more simple concepts to be able to build some valuable tools. You can pick up very little bit and get a lot of mileage out of it. So in this talk, I'll go over Lambda functions and how it fits in with step functions. I'll jump into the step functions and the service primitives that are available with it, and I'll go into how these can be used as solutions in a project and what general repository would look like. Finally, I'll go into hints I picked up for when the project gets a bit more complicated. So the name for this title sort of comes from the when you make the call, import this in the interactive terminal. I think there's some great general advice to be gleaned from there, and for some of the more Pythonic patterns, they can be applied to orchestrating with step functions. So just a show of hands, other than being Python engineers, does anyone host any workloads in AWS? Yeah, it's a fair amount, yeah. Anyone working with serverless, doing serverless stuff? Cool, yeah, about the same amount. And what about step functions, doing things with step functions? Yeah, a couple people. No, that's really good. So as you probably all know, Lambda and serverless have been around for a few years now, and you can get very far with it with just knowing a little bit of Python. It has a lot of positive things going for it. It's cheaper than hourly instance hosting. You don't really need to be concerned too heavily with configuration and the underlying environment to get started. I find that writing for Lambda functions encourages refactoring your code to be more modular and to operate for shorter time periods. And as I mentioned earlier, there's quite an easy learning curve. So obviously not everything fits into this pattern, but usually what I found you can do is with your deployment tools, use serverless patterns to manage the applications that can't be built with serverless. So an example of this is that I built serverless backup tasks, nightly on-off switches for your non-critical infrastructure, or serverless compliance tools. So if you're doing sys checking, that sort of thing. If you have a classic app in a server, you can orchestrate around it with step functions, manage the state of the server on the box with SSM run commands, and perform infrastructure maintenance tasks with stuff like Lambda and CloudWatch events. So the standard pattern for Lambda function code, if you've not used Lambda, the part of the service essentially has a referenced entry point where you can take in some arguments from an external service into a dictionary, usually labeled event, perform some work on the handler or call functions or modules, and, import it into the package and return some result. You can interact with the AWS service APIs with things like Bot03, do things like perform tasks useful to the cloud infrastructure. So cool story and all, but these are just basically individual task handlers. You can't really chain these very well, persist data, perform any like overarching control logic. So this is where step function sort of comes into use. So AWS Step Functions, it's a service that gives you basically a set of primitives that can be combined to perform actions in a controlled way depending on control logic between states. The primary object of step functions is the state machine. It's very similar to a formal state machine where you have a set of states with transitions connecting them, an initial state, a set of accepting states, and potential trap states. That's sort of where the analogy breaks down, though. The initial state variables are dictated by a execution payload when being triggered by an event, and each state has basically a few extra pieces of behavior that can be invoked. So what can you sort of use state machines for? I found to be really good at building and tearing down cloud applications with a factory pattern. You can use to perform end-to-end testing on your application deployment, so you can use it to tear things up, shut it down again. You can manage the bootstrap of AWS accounts with resources needed for your project. So like that's a couple of use cases off the top of my head. The service primitives provided by the service gives you control when you need to build systems like this. Essentially, any simple orchestration task that can happen within the span of a year can work in this framework. If your job takes longer than a year, you might want to just refactor, or you can also architect around it. So the available primitives for state machines, essentially those are the states. Each has its own type. These include wait states, which is basically just waiting for a fixed period. Choice states, where you can use inputs and outputs of other states to work out where the state machine should transition to next. Parallel states, which allow execution to occur between two or more branches of the state machine. You can use pass states to provide meta actions, like modifying the information being passed between states. The state you'll most likely use is for the task state. The state you will be using most likely is the task state that triggers an execution of some service integration. The most popular one I'll focus on is Lambda. Complete with basically this will be complete with inputs from previous states and outputs out to successive states. All of these can be augmented with exception try-catch logic or flow control logic, which I'll cover further on. Having this, you can see some pretty complex behavior can be expressed with state machines. You can set waiting loops, have contingency states when things fail, perform tasks in parallel. The main thing really, though, is as the name suggests, state machines provide the piece that was missing from Lambda, the ability to persist state between runs. So pictured here is an example of a state machine graph. These are auto-generated for you with the service. AWS step functions come natively with the graph visualization tool. This one here is one I've written for building our customer deployed environments. It will deploy our application, wait for the process to complete, then it tracks time to deploy and whether it was successful or not. If it gets a successful build, it'll then do a graceful termination of the environment to make sure that everything's wiped out, and then tracks the time for that also. And we can do things like map that in CloudWatch to make sure that our build times aren't blowing out, or if things are getting better, or if we're getting successes, failures, that sort of thing in regressions. So you can see in that graph there, you can see timeout, failure, success states, which dictate how the run of the machine. You can also do this tracking through CloudWatch and getting any regressions. So that's all well and good, but why would you use this? The service is highly scalable. It natively allows parallel executions, so it's listening for execution calls and can handle 1 million open requests. You can use step functions as the entry point into your logic for orchestration, and be able to handle edge cases when unexpected behavior arises. You're getting all of these benefits of using Lambda, as you've seen before. You're not wrestling with server configuration, operating system implementation details. Saying all this, you still need your CI/CD solutions, but you can easily move away from God boxes if you're still running those. You can set up lightweight agents that just have permissions to execute the step functions, which have permissions bound to their respective lambdas, so there's less chance of the permissions given to the agent being used in some unintended way. I might just quickly grab some water. So this is pretty cool. Step functions has a well-defined niche in orchestration of your service. If you were to build a project like this, what would it look like to deploy with best practices in mind? As engineers, we always want to automate everything as much as possible, so using infrastructure as code is the way to go. CloudFormation templates is generally your best option for AWS resources. Lambda service requires generating a bundle package containing your source code, so if you've used Lambda, you'll be familiar with this. The source and bundling functionality can be kept in the repository with your infrastructure definition. You can define an interface with your project repo with a make file with actions like build, deploy, install. This way, whatever is deploying your service has a common interface to work with. So with all this, your deploy script simply requires calls to AWS CLI from the make file to trigger the creation of your infrastructure as code. Even with just this project template, you can build a microservices framework where each state provides some orchestrated service and using these as factories to produce application resources. The factories can be deployed in a mirrored fashion in each of your environments for development, integration, staging, production, for testing purposes. So now you sort of theoretically have enough to start a project. Using these state machines as application factories, you get going with the best intentions. So, like some projects go, many projects before it grows organically. More features get tacked on to meet requirements. Very slowly, you end up with a bit of a beast of a solution with one or more of the problems listed above. A lot of pressures can be put on a project, quality can fall by the wayside, and best practices can go out the window to get a first iteration completed. So with all this in mind, what are some ways that you can do to simplify a complicated project like this? Here are a few recommendations based on what I've come across with serverless and step functions. Give some of these a try and revisit this if you find things getting complicated. So just standard project grooming. If you've been a developer for any length of time, you've probably heard about all these. Life is too short to worry about linting. I really like the Go pattern of enforcing formatting style. Black is really great way to do the same thing that Go does. The Henry Ford quote sums it up pretty well. You can have it any color as long as it's black. Obviously, you are doing unit testing, whether or not you're using just a standard library or something like PyTest or Hypothesis. As long as you're doing testing, obviously that's best practice. Set up your coverage reports to get an idea of how well your code is with tests. Your reports can be bundled with your releases. Even if you're not enforcing a coverage percentage floor, you can let people decide to use your release based on what's available and show you are performing due diligence. Git offers a lot of workflow automation and hooking, linting, and other types of checking into your source control solution can make these things happen as a course of your ways of working. So this one came up pretty recently. Another team member recently introduced automated release drafting and pull request categorization based off commit messages. So offloading project burdens to automation will definitely help out. So talking more specifically about step functions, you can define, defining a step function needs to be done in JSON, whereas CloudFormation can generally be in YAML. It's a little bit inconsistent, but it's not a deal breaker, but it's just something to be aware of. For choice states, if a variable referenced in your state definition is undefined in the JSON object, at that point, your state machine will stop. It seems to be because the coupling between the Lambda and the state machines, this can trip you up if there are any discrepancies between your state machine definition and your Lambda code, and you won't find out until runtime. On the state machine dashboard, this will come up as a halted state in gray. If you're running your state machine while there are other executions, sorry, if you update your state machine while there's executions, like with something like CloudFormation, the previous execution will continue to operate on the original version. Could be an issue with your service in deployment or with long-running execution. So if your old version has a breaking change, you may find that you might get inconsistencies. So all branches of your Lambda code has to flow to a return statement, passing back the results that go on to the next object downstream. You might get some confusing bugs if you have a branch of code that exists early on for some cases, but doesn't pass on the expected values downstream. So that's happened in the past as well. I've caught that one. So with long-running executions, my first real main tip is performing pre-flight checks. So for things that are lasting, for orchestration builds that are going for like 20 minutes, 30 minutes to build up a bunch of accounts, this is the first one. Verify your dependencies upfront with pre-flight checks. If you are managing a lot of dependencies, it's easy for resources to go missing, for some piece of infra to not be in place yet, like missing Amazon images, SSM parameters, that sort of thing. It's worthwhile checking up front before you run the whole thing and risk losing 20 minutes of your day to a dud deploy. This could also happen if you were working across AWS account boundaries. You may have expected some dependency to be present in a remote account, but find it might be missing. This will happen especially if you've got a bunch of mirrored accounts that are supposed to look exactly the same. It might be even worse, and you may be orchestrating in the wrong AWS account, even though you have a role there, which is good to know early so you can break out and see what happened. Pre-flight checking can be implemented as an initialization step at the beginning of your execution. You can do things like collect IDs of necessary resources, work out environment-specific edge cases, like your deployment environment runs extra tests or has verbose logging flags. You can validate the execution parameters and be certain that what's being passed on meets an expected contract. So the next one, managing data flow. Data flow is a big part of it, big portion of managing state machines. So here are a couple of general tips. As mentioned earlier, state machines communicate between states with JSON objects that translate to code, in your code as a dictionary. As you can imagine, keeping the objects small between states will simplify your state machine and make it easier to track what is happening state to state. You can manage this with state definition parameters with things like output path, which will limit the amount of the portion that gets sent into the state. So you can drill down to only have necessary values. Similarly, you can use the input path to the state definition to limit what goes into a state, which can help with maintaining contexts. So that's one way of making it so that your Lambda function has less to work with. Another solution is to actually just not pass things between states and have environment-specific stuff. So if you're using infrastructure as code and building your state machine with CloudFormation, you can do things like use the state definition parameters fields, which let you modify the state JSON objects in place with injecting into states at build time. This is useful if you have a test environment and you have multiple branches using the same resources. You can let the CloudFormation know about the branch that you're currently working on and pass the value into the state machine without having to pass it through passing it through the JSON payloads. You can store variables that are related to the account or environment that you're working in with Systems Manager parameters. Doing this, you can bind these variables to one place and make reference to them in other parts of your orchestration to not pollute your dictionaries. In the case that you need a lot of data, you can use S3 and access whatever you need there. So obviously, S3 will let you keep like terabytes of data. So if you need terabytes of data, you're probably not going to need this. But I mean, I don't know what your use case is, so sure, have at it. Data flow with parallelisms is another case that needs to be managed. When you use the parallel state primitive, it breaks down the state machine down into two sub-machine branches with their own copies of the input object. If you wish to share information between the two branches, you need to manage some shared medium which comes with its own set of difficulties. Each branch has a termination point, and each branch will block until the final branch has completed. Once the parallel state has completed, it is the job of the next state downstream to decide on what to do with the copies of the dictionary and pass along the result from there. So as an example of this, you might be checking for the success of both of the operations on your two branches. In each Lambda, you'll set a success you might set a success boolean on both branches that gets passed into the converging states. The converging state can then iterate over it with something like an OR statement to tell if all of the branches were successful. So this segues into the next set of tips involving parallelism in general. Step functions actually provides a few different ways of managing parallelism you can take advantage of. So what I described previously was the state primitive for parallelism, but there's which is a type of static parallelism. So an example of this is if you have a state machine that manages the bootstrap of an AWS account for you to use. you know the account needs an S3 bucket to manage configuration in a specific DNS-hosted zone put into the account. Each can be provisioned in a parallel state as neither has a dependency on the other. The parallel state can be used in this case. So the next way to handle parallelism is by nesting state machines. You can theoretically have concurrent executions of a state machine, so you can hand off tasks to another machine and have that handle each uniformly and pass back results through some shared medium. Where the previous method of parallelism is static, that is more dynamic because it's using cases where you don't know how many threads of execution you need at runtime. So this is a warning with this one as well. You could be very easy to hit API or resource limits using this, and you may find out a month later that you've been hit in the credit card. So AWS has put in activity workers recently as well. I haven't used those, but you can treat each state machine as activities where a manager process will hand off a token to a downstream worker process and then can block until the worker has returned. When it returns, it's a token that indicates completion. I'll skip over this one. I'll go into service exception handling. Your step function isn't executing in a bubble and is subject to service API limits. You might be aware of known exceptions that can happen in your automation. You may want to recover from those. Your Lambda might also take longer than you expect and time out. You might get generic exceptions where you might not know how to handle, but at the very least you would like to be able to track what happened and alert anyone responsible for operation. So step functions have native exception handling capabilities to allow retries when something's been raised. If you've designed for your process to be idempotent, you can implement subsequent retries and have follow-up attempts to perform a task and to be sure that it happens at least once. An example of this is checking to see if the resources a state is responsible for already exists. So in the snippet here, you can see a state definition that applies retry logic if the bound variable function has been running for longer than expected. It tries 3 times with 3 seconds as a base interval and does exponential backoff. Sorry. So some other examples, you can put in if the underlying service limits are causing issues, you can retry on those cases as well. And you can also put default logic in there as too. So you might not want timeouts to retry, but you may want that any other type of error to cause a retry to get thrown. Finally, with exceptions, you can try catch. So you can do if you get an error and you need to recover from it, and you know what it is, and you have a specific logic for it, you can use cases like this. So the next one is breaking your code out to libraries. So the great thing about the state machine is that it's comprised of a bundle of Lambda functions that operate like a standard Python module. So as with any project, you can make reference to any library you have available. You've pulled in through site packages, and you can bundle that into the code zip and make that available. If you have built out an isolated piece of functionality you want to use across multiple factories or services, bundle it up in your library and pull it in when building. So an example of this is if you had some wrapper helpers and for tracking purposes in Slack. So it would make sense that a few of these services may use this functionality. You can move this code over to its own repository, create its own setup py, and with the appropriate metadata, make it publicly or privately available. Once this is available remotely, you can pull these helpers into pipenv and can be bundled into your Lambda zip bundle. From here, you can then upload and reference them in your CloudFormation, integrating them into your orchestration. So this is very powerful, as you can get out of the box libraries that can be used across your state machines. If you have designed nice abstractions for your modular resources, libraries are a good place to store and reuse these. So once you get your code into a state machine and it's running and something goes wrong, how do you work out what happened? If you followed some of these steps up to now, things might be clearer. If you are working in a test environment, you can diagnose a lot of issues in the service. So the state machine graph is an excellent visualization tool. You can click states, get exceptions to jump to CloudWatch logs. There's the service dashboard, which I'll show here. This is the example that I showed initially with the CDE system. You can see the green states are in the successful ones. You can click through onto each of the states and get the input and output information JSON payloads. And if you click on the logs, you'll get a set of CloudWatch logs that are associated to it. There's also the execution trace history, which will show you the actual states that get run, and you can click through to get JSON payload information. Cool. So summing up, to finish up, AWS Step Functions is a very powerful service, and I like it for a lot of reasons. I think a lot of Python programmers would also appreciate it. Give it a go if you have any applicable use cases. I've given a rundown of what the service is, how it works, and some details of the service I didn't get when I first tried it. If you try it and the project grows, you might need to implement some measures to help scale it out, which I covered here. This wasn't a complete guide to step functions. It's a really rich service, but it's hopefully enough for anyone who's considering giving it a go. I've linked to the slides here for anyone who's curious. Is there any questions I can answer?
Just before we start questions, please thank Michael Kelly. We have time for 1 or 2 questions. We'll start over here.
You mentioned CloudFormation a lot. I personally can't stand CloudFormation. Are there any other tools to make your job easier?
So I guess I listed CloudFormation as this one just because it's cloud native. It's AWS native. So I just, for ease of use, we generally use it just because it comes out of the box with AWS. If you're using step functions and Lambda, it also just makes sense because it's all integrated in there. Other than that, you could probably use Terraform, but I haven't played around too much. I couldn't comment.
Are there any other questions? Yes?
Just an easy one. Is that 15-minute limit per state or for the whole thing?
That's per state.
Okay, that's good.
So yeah, you can. That's the timeout limit for a Lambda function. You have a whole bunch of linked up Lambda functions. If you hit a timeout state, you can then do retry logic to try again if you didn't get the thing done in that 15 minutes.
Any other one? Yep.
Thanks, that was really interesting. You mentioned about passing data from one state to the next, and you said sort of a little bit of data or terabytes going to S3. Can you give me an idea of sort of where the line is? I'm thinking of a sort of use case where you pull a bunch of data and then sort of want to process it for 4 different cases. So yeah.
Yeah, if you're doing terabytes of data, I probably wouldn't recommend this service for that, sort of for Lambda pretty much. But in terms of passing data between 2 states, that's in the kilobytes range. So you won't be able to pass very much. Really, you'd be using S3 if you're going to go over that value.
Cool, thank you.
I think we have time for one more question. Yep.
Thank you very much. How do you go about testing the overall state machine? And step
Sorry,
function?
what was the last bit?
How do you go about testing the overall state machine as well as the individual? So the individual lambdas you can test on their own, but the overall state machine is quite a big complex thing. Are there any kind of good ways to test that automatically?
So in my case, what I've done is I created another state machine. So it's turtles all the way down pretty much. But for the thing that you really care that executes correctly, we'll have a nightly run that will basically within every n hours, it will run it'll run the orchestration for you and then bring it up, do some metric tracking, and then shut it back down again. So it's just running through the executions in different ways. We do there's a couple of different ways, yeah.
Thank you again, Michael.